We're talking about invariant prediction for generalization in reinforcement learning. Great. Yeah.
Great. Okay. Can everyone see and hear me and see my screen?
Yes.
Great. All right. Cool. So thanks for the introduction. Yes, my name is Clare Lyle from the University of Oxford. I'm going to be talking about recent work that we presented at ICML this year called Invariant Causal Prediction for block MDPs. This was joint work with a number of really great collaborators, but in particular, I'm going to highlight Amy Zhang, who is speaking right after me at this workshop, who is co-first author on this paper. We have code on GitHub, and there's an archive link here, or you can just Google Invariant Causal Prediction for block MDPs, and it'll come up. So the sort of motivating problem for this talk is something that technically isn't RL, right? So RL is all about maximizing your reward within a single environment. But in practice, when we're thinking about what role reinforcement learning agents are going to play in the world, it's a lot easier to think about the types of environments they might face as more like a family of MDPs. So Chelsea Finn sort of touched on this at her talk on meta learning. So basically, the problem that we're thinking about for this paper is you train your RL agent on a couple of environments. So like you want your Majoko agent to be able to control the half cheetah, but you can imagine that in the real world, if you're feeding it a pixel valued input, the camera might get jostled. So even though the physics of the world are staying the same, the data that it's getting as input might change slightly. And ideally, we would like to know that when we deploy our agent in the real world, if someone bumps its camera and it starts seeing a new angle that it's never seen before, it'll still be able to execute the policy that it learned in the training environments. So if you apply most standard deep RL methods that are sort of like well known today on this type of problem, if you don't give it like on the order of potentially thousands of training environments, it's really going to struggle to generalize to this new environment, which makes sense. We trained the RL agent to do really well in one environment. Why would we expect it to do well in another? But the problem is that this happens even when the new environment is like sort of causally equivalent to the old environments. So in theory, the agent should be able, if it had the right representation, to take the knowledge that it picked up in its training environments and apply it in its test environment. So a very short summary of where this talk is going to go. So our goal is that we want RL agents that can generalize to new environments where the underlying MDP is the same. The way that we're going to do this is by trying to find a representation that maps sort of equivalent observations from the different environments to the same sort of like true state in the underlying MDP. So the way that we're going to find this representation is by stealing an idea from the causal inference literature called invariant causal prediction. And basically, like because we've assumed this extra structure of the underlying MDP being the same, the problem becomes a lot easier than meta or transfer learning, and we're actually able to get, in some settings, really nice guarantees. So at the crux of this idea is the state abstraction. So I'm going to quickly define a state abstraction as basically any function that takes the state space of your MDP and maps it to some other space. So ideally, this mapping is going to simplify your states in some way. So it might group them together if you're dealing with a tabular setting, or it might be a map from a high dimensional pixel valued observation to a low dimensional latent representation in the case of a deep neural network. But we're also going to want our state abstraction not just to be any arbitrary function, but to satisfy certain properties. In particular, we're going to be interested in model relevance. So this is highlighted very nicely in Leihong Li's paper towards a unified theory of state abstractions. Basically, a model relevant state abstraction is something that preserves the reward and the transition dynamics of the MDP. So we can imagine if we basically had some sort of chain environment where you basically dropped from S1 to S6 and then get some reward at S6, we can sort of group together states that are at the same level horizontally and still preserve the transition dynamics and the reward structure of the MDP. In deep RL, the case becomes a little bit more complicated, and I'll mention it here because this is the deep RL workshop. So the canonical state abstraction model says we have some input space X that gets fed into some state abstraction phi, and on top of phi, we're going to learn some value function V. The problem is that in deep RL, we have some neural network that's our function approximator. And a neural network you can think of as basically a sequence of compositions of functions. So there isn't really a canonical layer where you can say, yes, at layer K, I have stopped being my representation, and now everything after this is computing my value function approximator. So basically, when you see later on our results for the deep learning setting and learning representation in deep learning, we're basically going to sort of arbitrarily fix some layer of the neural network, and we're going to call that layer the representation, and that's the layer that we're going to be feeding in auxiliary losses to. So the second part of this setup is really about, okay, so now we know what like a good state abstraction is. How do we define behavioral equivalence? So ideally, we would go into sort of like the definition of sort of bisimilarity, which is like the sort of more rigorous way of defining behavioral equivalence. You can also sort of characterize it in terms of state abstractions by basically saying our family of MDPs are going to be behaviorally equivalent if there exists some state abstraction phi, such that the image of each state space under phi is the same. And if we look at phi over the union of all of these MDPs, it's a model relevant state abstraction. So our goal here is basically to hopefully learn phi from a relatively small subset of all the possible environments. Technically, I've written out M1 through MK here. Maybe we actually have an infinite set of environments, in which case we definitely need a very small subset of the environments to be able to generalize well. So an example might be if you're training a robot to do your dishes, you do a redecoration of your kitchen, but you leave everything in the same place. You just change the wall and the cupboard colors. You ideally don't want every time you repaint your kitchen, your robot to have to learn how to wash the dishes from scratch. So we definitely want like sample efficiency in contexts like this. For another example, you could think about sort of a board game playing agent. So maybe you want to figure out how to map different chessboards to the same sort of true board state. So you would want your starting position in all of your different chess pieces to map to the same latent representation. But in particular, because we're doing this relatively strict assumption on the behavioral equivalence of the different environments, we're not really going to care too much what happens if we try to apply this state abstraction to some new environment that isn't behaviorally equivalent to the old environments. So like if we took our representation that works really well for chess and try to feed a backgammon board through it, we don't mind if the representation that we get as a result is totally nonsensical, because we're not really evaluating ourselves on that setting. So to understand how we're going to find these state abstractions, it helps to think about the RL problem as sort of a causal graphical model. So causal graphical models, basically you have nodes and you have edges, and edges indicate sort of conditional dependence, sort of directed in time. So like if I change ST, that affects ST plus 1. So the idea here is this is pretty much the familiar RL problem. We have actions that affect your next state, that affects your reward. Then you have your next action, and then your previous state feeds into your next state along with the action, and you get a reward. And you keep on doing that ad infinitum. The key observation that we're making here is we're sort of distinguishing the true state into what we're going to call a causal component and a spurious component. So this is basically saying any component of the state that is going to affect the reward at some point in time, we're plugging into S. Everything that's sort of random noise, we're plugging into eta. So eta can be correlated over time, but it's sort of independent of the reward. So there's no way of like following arrows from a to t to get to RT prime for any t prime. So we're going to sort of take this insight that we have that basically we can view the, one important thing as well is that we can sort of therefore, like in the framework of model relevant state abstractions, say, okay, well then basically like ST is sort of determining the reward and the important transition dynamics of the MDP. And A to T, we can sort of change and have it be whatever. So in our context, we're basically loading all of the changes between the environments into A to T and saying we can basically ignore this. We really care about ST. So basically, finding a good model relevant state abstraction, we can sort of think is basically trying to figure out what is ST. So to do that, we're going to use a tool from the causal inference world called invariant causal prediction. And this is basically a method that takes data from a bunch of different environments, where each environment is generated by intervening on the data generating process in some way, and gives you a sort of set of variables that it thinks are causal parents of the thing you're trying to predict. So the key insight that they make is basically this equivalence between causality and invariance. So if I'm trying to predict some variable, say I'm trying to predict the reward, and I'm trying to predict it using another variable, say eta, that is not a causal parent of the reward, then if I intervene on eta, the relationship that I learned initially between eta and R isn't going to hold anymore. So basically, I'm going to see that the distribution of errors that I get from one environment to the other is going to change. So basically, that change is sort of the idea of like the invariance principle. So if I were depending on the parents, then I would be invariant to these interventions. Whereas if I'm depending on something that isn't a parent, then I sort of will not be invariant under these interventions. So to sort of give like an intuitive example, if our state just has two components, x1 and x2, and x1 is the only component that will ever affect the reward, then if we sort of initially train a value function predictor on x1 and x2, we might not necessarily assign value 0 to x2. It's super unlikely that our optimization procedure exactly assigned like 0 reward if we were doing something like linear regression. So basically what we can do instead is say, okay, well, now let's train on two environments. I'm going to assume that in the second environment, there was like some sort of intervention on this distribution. So maybe I fixed x2 to be something. Now the relationship between x2 and the reward is going to change. So the error that I was getting in environment 1 is going to be very different from the error that my predictor now gets in environment 2. And this is basically the procedure that invariant causal prediction uses to identify causal parents. So we make sort of one assumption that is a little bit stronger than the normal Markov assumption in RL. So normally the Markov assumption in RL says x1 and x2t are independent of x1 and x2 sort of t minus k, given x1 and x2 t minus 1. We're going to assume something slightly stronger, which is basically that if you have sort of if you have x1t and x2t, then they're conditionally independent of each other, given x1t minus 1 and x2t minus 1. So basically, this is just saying that there's no like hidden mechanism generating our MDP that's like correlating them beyond whatever they would get from the previous state. And the second assumption we make is that the training environments correspond to interventions on variables in the latent MDP. So the main takeaways are sort of number one, that which we've hinted at already, is that the sort of causal component of your state corresponds to a model relevant state abstraction. And in particular, if your state corresponds to the set of variables in the causal graph that's sort of responsible for your MDP, then just taking the subset of the indices that correspond to the causal variables is basically enough to give you a model relevant state abstraction in any MDP that's now generated by interventions on eta. So this is really nice because it basically means that we can directly apply the ICP algorithm to the RL setting to find a state abstraction that's sort of going to generalize basically perfectly to any other MDP in our family, assuming that we had sufficient training environments. And in certain settings, like if the transition dynamics are linear with Gaussian noise, then we basically need on the order of the dimension of the state training environments to identify the causal ancestors of the return. So this is way better than what you would get if you didn't have this assumption on the equivalence, because now we basically can say, okay, well, because I know that any environment I'm going to see in the future is related to these environments in this very specific way, then basically once I've identified the causal variables, I'm done. So we've turned a problem of learning into a problem of identifiability, which is much more sample efficient. In the rich observation setting, running a bit low on time, so I won't be able to go super in depth here. But basically, we can't get really guarantees anymore. But we can sort of take the intuition behind this invariant prediction idea and try to apply it to our representation. So basically, we take some sort of representation model phi, and on top of it, we're going to be training something like soft vector critic or TQN, but we're also going to have this auxiliary model, which is sort of trying to get phi to be a model relevant state abstraction that's invariant across the different training environments. And we're going to hope that by forcing it to be invariant across the different training environments, it's going to sort of be picking up on the causal structure that we want. So basically, the key components of this model are we have a reward loss that's basically telling us, okay, we need to capture the reward. We have a transition dynamics loss that's telling us we need to capture the transition dynamics. Here we sort of split things up. So we could have had a transition dynamics model on just the sort of latent space. But the problem there is that you can get these like weird sort of like pathological solutions where you just map everything to 0. So we instead decided to basically have this grounding in the real world where we sort of have an additional model that can sort of take over all the environment-specific information that might be needed by the decoder. And then finally, we're also sort of doing adversarial domain classification on the representation learned by the invariant encoder to basically say that the representations in latent space of each of our environments should overlap as much as possible. So empirically, we do find that this works pretty well. I am running very short on time, so I'll keep this like relatively brief, but basically we compare against sort of 2 ablations. So the question that we really want to answer here is like the thing that is making us generalize the invariance, or is it just that we happened to come up with a really good auxiliary loss? And basically what we find is, so if we just train our model with a single decoder, which is basically exactly this, but now instead of having sort of task-specific information, we're letting the invariant model pick up some task-specific information. Then we see like much worse generalization. If we only train on one environment, it's even worse. So this is in a really simple sort of model learning task where you're just trying to predict the next state of an agent interacting with the MDP. We also, as a sanity check, compared against IRM. IRM, invariant risk minimization, is sort of another approach to invariant causal prediction. It was targeted more at the supervised setting when it was proposed. And we found that it was very difficult to find hyperparameters that would sort of make it work. So in a lot of the settings that we tried it in, it just sort of like didn't really converge to anything very competitive. We also evaluated model learning for a linear predictor in the setting where our theory tells us we should perfectly learn the right state abstraction, and we find that indeed, basically, as we intervene on different variables in the MDP, as we intervene on the spurious variables in the MDP, we find that a predictor that's trained on the ICP representation basically doesn't matter how far you push the spurious variables away from the training distribution, it still predicts perfectly well. But a model that was just trained on the full state space using a least squares predictor does quite terribly as you shift the input distribution further from the training distribution. So we basically repeated a similar experiment for imitation learning. So in this experiment, we were varying the background color. So we train with 2 different background colors and we evaluate on a third. Here we train on 2 different camera angles. So this is basically the Mujoko half cheetah with different camera angles from the first slide of this presentation. And we find again, basically that enforcing this invariance really helps reduce your generalization error. Although we note that we do still see overfitting, which kind of makes sense in this setting because trying to sort of be invariant to all possible camera angles, given that you only train from 2, is a pretty difficult task. And finally, we look at the reinforcement learning setting. Wrapping up now, don't worry. So we basically see again, training with this like invariant representation, you get a much smaller generalization gap than you do if you just trained a regular SAP model. Right, so in conclusion, we've basically shown that invariant prediction is super useful for finding state abstractions that can help you generalize new environments. We've shown some results on how to find these state abstractions and how they generalize. And we've shown in the rich observation setting that just trying to get your representation to be more invariant improves your performance on new environments and range of tasks. All right, thank you all, and I'm happy to answer any questions.
Yeah, excellent, thanks. Yeah, so we have time for questions. Any questions from the audience? Well, maybe I can start with a question. Perhaps I'm missing some details, technical details, but I'm curious what whether this work somehow compares to an earlier work by Peter Stone's team in about, I forgot the time, 2000 something, with Nick John on predicting irrelevant state variables using various kind of hypothesis testing. The setting is that you have a long state vector and you want to discover which ones are relevant, which ones are not. They use some kind of hypothesis testing to identify which ones are relevant. Is it somehow related? And have you, can you say something about it?
Yeah, so I haven't read that paper, so I can't say a lot about it. I will say that that's sort of effectively exactly what our method for the sort of like exact observable variable setting is doing. Where basically, I guess the trick here is that we sort of are leveraging the multiple environments. So rather than just saying in a single environment, we're testing whether sort of this variable is independent of the reward. We're really sort of looking over like all of these environments. We're doing a hypothesis testing on the induced distribution of errors, like predicting the return. But it sounds quite similar. It's like the same idea at the core. It just sounds like a difference of like, are you looking at multiple environments or are you looking at the single environment?
Okay, I see. And then I noticed that you have an assumption in assumption 1, if I remember, in the talk that says you require the observation to be fully Markovian. Right, yeah, it's fully observable and therefore it's Markovian. Is there, have you tried at least empirically to see how sensitive the approach is when this assumption is slightly violated?
So I think like in principle, it should still work. Like this method would work in theory, I think under some settings of partial observability. The main thing that we were really trying to avoid with assumption 1 is sort of there being hidden variables that are sort of affecting this like t-1 to t of like these sort of like different indices of your state. So basically, ICP does in theory sort of, I think you can sort of get it to work with like some hidden variables. So in theory, it should also work in settings where you sort of have like a PUM-TP. But we were mostly, it's a lot easier to do the analysis when you assume you can observe everything. So for our purposes, we just sort of assumed like a standard RL setting.
Right.
But yeah, that's a super interesting area for future work.
Sure, yeah. So I noticed that Traba also mentioned something in the chat. Tom Dietrich has also worked on this irrelevant state variable detection in RL. Yeah, that's.
Yeah. So this is super related. The question that we're really interested in is sort of like finding relevant variables that you couldn't find in the single environment setting, and sort of like really trying to get rid of those. But yeah, it's like very similar.
Yeah, right. So there's a discussion in the panel to trying to locate what paper it is. Chava, do you remember which paper?
No, I need to look it up.
Okay, yeah, no problem. Thanks. And then we have a question from the audience. Claire, could you see the QA tab?
Yes.
Okay.
I'm clicking on it, but it's not doing anything.
Right. So the question is for Claire. So correct me if I'm wrong. For one of the ablations cases, this is done for the model-free settings, and the causal bounds are used for a priori for the basin settings.
So none of these cases are necessarily Bayesian. I guess the question you're sort of getting at is sort of what's the yeah, I'm not quite sure if I follow the question. So basically in all of these cases, we're doing sort of frequentist hypothesis testing. The main difference is it's a lot easier to sort of learn use the sort of like model learning loss rather than just trying to do sort of like the type of algorithm, like trying to immediately translate the type of algorithm we have in the fully observable variable setting in the rich observation setting. So for us, we just found it a lot more stable to basically try to use a model learning task as the auxiliary task that we were trying to sort of enforce invariance through. I hope that sort of answered the question.
I have a quick question if there's time. Hi, Claire.
Hi.
So it seems, I wonder in practice on a lot of problems, are you actually going to find things, do you think, that are completely irrelevant? Or do you think that there's sort of a more complex factored structure where, you know, maybe there's like 3 different sources of reward essentially, and, you know, some variables are sort of irrelevant for some of them, but not for others. And you can't really make much progress without sort of factoring and separating those. And or do you have any thoughts about how to do that, or have you thought about that?
Yeah, so I think that's super interesting, is sort of getting at like, because ideally what this work is sort of doing is saying like in an ideal world, we would be able to sort of learn some sparse factor graph that's like corresponding to the sort of true causal structure of the world. But that's really hard to do. I don't know of anyone who's succeeded in doing that yet. So let's just sort of assume that like if we got a bunch of different data from different environments and we sort of learned something that is like sort of ignoring the differences between those environments, then it's going to similarly ignore the differences in new environments that sort of exhibit similar structure. I think there's like loads of examples in the real world where there are components of your state that you just want to completely ignore. Sure. So like a bunch of stuff about like how your data is collected, right? So like the camera angle is example. You like really don't want to depend on the, like you can basically throw away the camera angle once you've sort of captured the location of all of your limbs. So I think like to some extent it's safe to ignore like most of the factors or like a lot of the factors that vary between your environments. And yeah, I think you can come up with like a decent number of like realistic-ish examples where that works. Or at least that the information that you throw away is like less helpful than the generalization performance that you gain by throwing away that information.
Cool, thanks.
Terrific. So it seems that we're right on time to move to the next talk if there's no more question. Then our next speaker is Amy Zhang from Mila. Amy, could you share your